Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we discussed about the Castiglione's theorem. I hope that you remember that thing, and we solved one numerical problem by using Castiglione's theorem. Now, today we will be solving one more numerical problem using Castiglione's theorem, and that is very typical actually. And you will appreciate that how easily it can be used. I mean, that Castiglione theorem can be used to determine the deflection of a slender member. Okay. Now, let us see. The problem is simply supported say beam which is having uniformly distributed load, say W naught per unit length. Okay. So, that is a simply supported beam, one simply supported beam which is under uniformly distributed load, say W naught per unit length of the beam. Now, I need to find out, so this is a point A, B, I need to find out the central deflection of the beam, say at C. Okay. So, this is your L by 2 and this is also your L by 2. So, total length of the beam is say L. Now, as per our Castiglione's theorem, if you recall, Castiglione's theorem says that if you manage to get the strain energy for a conservative system, okay, and I mean in terms of different forces, right. Now, if you want to find out the deflection, okay, along a line of direction of a particular force, then that will be equal to the partial derivative of your strain energy with respect to that particular force, right. Now, here if you look at this problem, in this problem we have some loading on the beam, okay, that is some uniformly distributed load, but I want to find out the deflection at point C, the central deflection, right. This is my objective. But at that particular central point, say at point C, no concentrated force is acting, right, okay, with respect to which we can go for the partial derivative of the strain energy, right. And we know how to find out the strain energy for this kind of system, but we cannot take the partial derivative with respect to some force which will be acting at point C. So, therefore, we will consider, okay, so that we can use our Castiglione's theorem, we will consider one fictitious force, a P. This is some fictitious force. So, this force is not there, some imaginary force. Okay. So, P is a fictitious load, okay, that really does not exist, but we are considering so that we can now, if I get the strain energy with respect to all these forces whatever are acting on the beam, okay, and if we take the partial derivative of that total strain energy of the system with respect to P, that will be giving me the deflection, central deflection delta C, fine. Okay. So, now I mean what is your first job for this kind of problem? Find out the support reaction, and you know how to find out. So, RA and RB, because due to symmetry it will be same. So, P plus W naught L, this will be also equal to half into P plus W naught L, fine. So, these are the reactions. Now, we will be considering two sections, say section 1 and section 2. For section 1, so this is your section 1, this is your say bending moment. I am showing only the bending moment. Of course, shear force will be acting, but we are not considering the strain energy caused by the shear force, because that will be negligible contribution towards the total strain energy. So, therefore, we are neglecting that. So, this is your RA, and you have uniformly distributed load W naught, and this distance is x. Fine. So, your bending moment expression, as you know, RAX minus W naught x square by 2. So, if you put the value of RA and if you simplify this thing further, so you will be getting half into Px minus plus W naught Lx minus W naught x square. Okay. So, this is the expression of your bending moment for section 1, which is valid from 0 to L by 2, which is valid from x greater than 0 less than L by 2. And if you, this will be required, as you know, del MB del P. If you recall the previous numerical problem whatever we had taken, so there we required that had calculated this magnitude, okay, or expression, right, del MB del P. So, that will be coming as x by 2. Okay. Now, for section 2, so we will be taking from the right hand side. So, as I told you that whatever direction you consider, left hand side or right hand side, that is not, that is immaterial actually, right. So, we will be considering the right hand side to make our life simple. So, this is RB, this is the section 2, this is your MB, and this is your uniformly distributed load W naught, and this length is L minus x. Okay. So, if you calculate MB, that is equal to RB into L minus x minus W naught L minus x whole square by 2. Okay. So, if you simplify by putting the value of RB, so that will be equal to half P into L minus x plus W naught L into L minus x minus W naught L minus x whole square. So, this is the expression of MB for section 2, which is valid from L by 2 to L. Okay. So, we can similarly find out del MB del P, which is equal to, from this expression, it is very much clearly written as L minus x by 2. Okay. So, now if I want to find out the deflection delta C, what we can do as per our Castiglione's theorem, delta C is equal to, if you recall, MB by EI del MB del P dx, right. So, this is your delta C as per your Castiglione's theorem. So, now for the whole beam we can divide like that, 1 by EI 0 to L by 2 for section 1, which is valid. So, MB expression already we have got Px plus W naught x Lx, W naught Lx minus W naught x square, and del MB del P for section 1 already we have calculated, that is x by 2 into dx plus 1 by EI L by 2 to L. Now, for section 2 to MB is this, so half P into L minus x plus W naught L into L minus x minus W naught L minus x whole square, and del MB del P is given as L minus x by 2 dx. Fine. So, this is the expression for your delta C. So, now if you look at this expression, okay, this expression is containing both load P as well as uniformly distributed load W naught. But frankly speaking, as per the problem, W naught really does exist, but what about P? P was a fictitious force, and that we have imagined, right? We have considered a fictitious load P. So, P actually really does not exist, right. So, we can make P equal to 0 in this expression. So, if I make P equal to 0, then the expression will be 1 by 4 EI 0 to L by 2 W naught Lx minus W naught x square into x into dx plus 1 by 4 EI integration L by 2 to L W naught L into L minus x minus W naught L minus x whole square into L minus x into dx. Now, you perform these two integrations, you will be getting delta C is equal to 5 W naught L4 384 EI. Now, if you look back, the same problem we have solved earlier by using your method of superposition. There also we had got the same value, right, 5 W naught L4 by 384 EI. Now, this is the way you can solve the deflection problem by using Castigliano's theorem. Is that clear? So, this is a very typical and interesting problem, and you see that very easily you have got it. So, whenever first you identify that at which point you want to find out the deflection, at that point is there any load or not. If there is no load, then you consider some fictitious load, and later on you can put that fictitious load equal to 0. Similarly, if you want to find out the rotation at any point, okay, and if you see that actually the moment is not applied at that particular point, and you know rotation will be caused by the moment only. So, you consider some fictitious moment and you do the same process, you follow the same process, okay, and you finally you put your fictitious moment equal to 0. So, you will be getting the rotation caused at that particular point, okay. So, with this I conclude this chapter, okay. Now, we will move to the next chapter, that is your buckling, okay, instability and all. So, let us come back to that part. So, let us see what is instability, okay. Now, in this particular chapter, we will be discussing about the concept of elastic instability, okay. If you look at this PPT, okay, concept of elastic instability, introduction to column buckling and Euler's formula, okay. So, these things we will be knowing that, okay. And what is instability basically? In the mechanics, what do you mean by instability, okay. So, if you look at these figures actually, so in this figure A, okay, So, this is a body O, which is resting at point O. Now, you take this body in this location, in this position, and leave it. What will happen? It will come back to its original location again, right, at point O, and this is called stable equilibrium. So, this is called stable equilibrium. Okay. Now, if you look at this figure, I will come back to this figure later on. The figure B will be coming back later on, but let us see the figure C. What is happening here? Your body was here at point C. Now, you have taken the body at this location and leave it. What will happen? It will not come back to its original position, right? Rather, it will further deteriorate the system. That means, it will go to the unstable situation, right? And this situation or this equilibrium is known as unstable equilibrium. Okay? That means, the body was under equilibrium, and if you try to disturb that body by putting in different locations, if it comes back to and you leave it, if it comes back to its original position, that will be called as your stable equilibrium. That means, you cannot disturb the equilibrium, right, stable equilibrium. But in this case, okay, in this figure C, I mean the body was initially under equilibrium, right, but due to some perturbation, okay, so the body is not coming back to its original equilibrium, right, and the body is going further away from the equilibrium, and that type of equilibrium is known as unstable equilibrium. Now, if you come back to this figure, figure 2, what is happening here? Your body was here, you are taking the body here at some new location and you leave it. So, here the body was under equilibrium. When you are taking the body here, that is also, I mean, providing some equilibrium. So, it is not coming back to its original equilibrium position, but in the changed location also it shows your equilibrium position or the equilibrium condition, right. That kind of equilibrium or the situation is known as neutral stability. That means, it does not depend on the perturbation or the disturbance. Okay. So, now with this background, if I try to find out the elastic stability, what do you mean by the elastic stability? Okay. So, if you look at these two figures, okay, this figure as well as this figure. So, there is a say vertical member, some vertical slender member say, okay, it is under the load P, P can be compressive or tensile. Okay. So, in this case compression, in this case tension, but if due to this application of the load, if the body or the slender member is taking the position like this, right. So, that means your equilibrium thing is not stable. So, this is your unstable situation, right, and this is quite common phenomena, particularly if you talk about the column, okay, or if you talk about the slender member, slender shaft in the machine, if you talk about the say aeroplane wing or something like that. So, basically all those slender members might be experiencing some kind of instability, okay, due to the application of the load or the direction of the load and so on. Now, we need to, I mean, if you talk about the column, right, in that is quite common feature you have seen in any civil engineering structure, that is a say column, okay, long vertical column. Now, if you apply the load on the column, okay, at certain point or certain magnitude of the force, actually vertical force, the column will not show any kind of instability. As you go on increasing the load, and suddenly you will see that column will be buckling, right, and that is causing the instability in the column at that particular loading. Okay. So, we have to find out that load where the instability gets initiated. okay, and that load is known as your critical load. Okay. So, let's talk about that. Now, if you have one unstable structure, suppose this is one unstable structure under this load P, okay, and what we are talking about, as I told you, that critical load, that P has say for example, so P has reached the critical load. So, once it is reaching the critical load, so basically it will cause the instability in the system. So, this is your unstable say structure. Now, if you want to stabilize this structure, okay, if you want to stabilize the unstable structure, what you can do, you can give some lateral support that you are providing by these two springs. Okay. So, these two springs will try to give the lateral support, so that the vertical member will not sway in the lateral direction or will not go to the instability. Okay. So, now let us analyze this thing and let us find out the critical load, that under this situation, okay, what should be the critical load. Okay. So, if you look at this figure, okay, and if you try to draw the free body diagram, now in this particular chapter we will be talking or we will be drawing the free body diagram at the disturbed state, not at the original state. So, this is your disturbed state. Okay. So, this is your disturbed state, means after your instability is getting initiated, you are drawing the free body diagram. Okay. So, this is the member. So, this is the vertical force which is acting on the member, and these springs, the spring constant, identical spring we are considering, spring constant is say K. So, therefore, you will be getting the free body diagram like this. So, this spring will be under compression. So, you are getting a compressive force Kx. So, x is the distance of movement from the original position to the unstable position, okay, disturbed position. So, that is the distance. Okay. So, this is your compressive force, this compressive force will be getting exerted by the spring on the right hand side spring, and the left hand side spring will be experiencing a tension, and that is why you are getting Kx in this direction. Okay. So, now if I want to find out the moment, okay, if I want to find out the moment with respect to point B means here, okay, if I want to find out the moment with respect to point B for all the forces, then what we will get? The upsetting torque, okay, if you look at the figure, the upsetting torque will be how much? That means which will try to cause the instability in the system, that will be how much? P into x with respect to B, okay, with respect to B, fine. Now, this upsetting torque or this upsetting moment, okay, will be getting balanced by the restoring moment or the restoring torque, okay. That restoring torque will be provided by the springs, right, both side spring. So, that will be how much with respect to, of course, with respect to B, because the support reactions at B, okay, the contribution of the support reactions at B in this torque calculation will be simply 0, because we are considering the point B for calculating the torque. So, the upsetting torque will be Px, whereas the restoring torque, that means which will try to pull back the system to its original position, or which will resist this kind of upsetting or the disturbance of the or the instability of the system, that will be how much? Twice Kx, that is the force, into L, that is the length of the member, right. Now, if from the problem itself, from the figure, you can realize that if Px is less than twice Kxl, that means the upsetting torque is less than your restoring torque, then what will happen? There is no problem, that is perfectly stable situation, right. Now, if Px is greater than twice Kxl, then what will happen? The system will go to the further deterioration, that means completely unstable situation, and that kind of thing is unstable. That means if you gradually increase P, okay, so suppose P equal to 0 and you gradually increase P, after certain time, I mean initially you will be getting this relation, right. So, Px is less than 2kxl, that means till that point it is stable. Then when you are getting this kind of relation, that is Px is greater than 2kxl, immediately the member will try to go to the unstable situation, unstable condition. Okay. So, therefore, the borderline between stability and instability can be defined as occurs when your P x equal to 2kxl, that means restoring torque is equal to offsetting torque. At that situation, that is the borderline situation, that means if you further increase P, it will go to the instability. Okay. If it is little bit lesser than this P, then your system will be completely stable. So, this is the borderline situation. So, this P is equal to twice KL. Okay. So, now this P is known as critical load or buckling load. Okay. So, this is the borderline situation. So, up to this, if you increase P gradually up to this P critical, there is no problem, system will be completely stable. Once you cross P critical, then your system will be going to the unstable situation. So, as an engineer, you should know what is your critical load for a particular system. Okay. So, if you don't know about that critical load, you will be going on increasing the load and ultimately you will be facing the instability in the structure. Okay. So, I will stop here today. In the next lecture, we will be continuing the same discussion on the buckling load. Thank you very much.